In the previous lecture we were discussing about the thin film boundary conditions at the interface in terms of the tangential force balance and the normal force balance. We have not discussed about what are the kinematic constraints at the interface. So, that will be reflected through a boundary condition called as kinematic boundary conditions. So, for kinematic boundary condition we have to see that say the interface is now like this, after some time the interface evolves like this. What remains unaltered from this configuration 1 to configuration 2? What remains unaltered? So, let us say that at a given x dash the interface thickness is h dash, and at the same, so after some time at the same x h dash becomes different. So, this is a combined spatio-temporal change in the film thickness. Over a period of time the interface topology changes in general altogether, and that makes h as a variable which is a function of not only x, because of the variation along x it is a function of x, but h itself is a function of time. So, that makes it as a combined function of position and time. So, to assess that combined function we define a variable f naught f dash, which is y dash okay. So, clearly if the interface is flat, at the interface these two are equal. Now, if we are located at the interface on a flat interface, if we are located on the interface, then y dash is equal to h, right. If we are located on an interface where this h itself dynamically evolves, we can say that our absolute location will change, but what will happen is if I am a particle, if I am located on the interface, I will still be located on the interface forever, but I may go to a different position. I may go to a different position, but I will, if I am located at the interface, I will be constrained to be located at the interface forever. This of course gets violated if there is a exchange of mass between these two phases, right, but that is not what we are considering here. So, if we are not considering that here, then what it says is that a particle which is located on the interface will be located on the interface forever, and this is the physics of kinematic boundary condition. So, that we can write equivalently as total derivative of f is equal to 0. So, if the total derivative of f is 0, we have expanded the total derivative in terms of the unsteady term and the advective term. So, now if we write individual terms, so what will be del f dash del t dash? That will be minus of del h dash del t dash, right. V dash is u dash into unit vector along x plus v dash into unit vector along y, and grad f dash is equal to I what is del f dash del x dash? So, that is minus I del h dash del x dash, because y is not a function of x, right, h is a function of x, plus j del f dash del y dash, that is derivative of this, that is 1. So, v dot grad f, what is that? So, u dash, so this with this dot product will make it 1 minus u dash and this with this is plus v dash. So, this boundary condition will lead to right. So, that means you have v dash at the interface this is the kinematic constraint that must be satisfied at the interface. V is equal to del h del t plus u del h del x. This boundary condition must be satisfied at the interface. So, let us take an example of kinematic boundary condition. Let us say that we have a rigid interface as the bottom wall. Okay. So, if you have rigid interface at the bottom wall, f dash is y dash, h is equal to 0, right. So, in that case, if you consider this version now, del h dash del t dash is equal to 0 because h is itself 0. U dash del h dash del x dash, first of all this is 0, on the top of that because of no slip boundary condition u at the surface is 0. So, that means you are left with v equal to 0. This is the no penetration boundary condition. So, the no penetration boundary condition can be perceived as a special case of the kinematic boundary condition. it is not anything different, it is just a special case of kinematic boundary condition, that any particle located on the wall will be located on the wall forever because it cannot penetrate through the wall. Okay. So, let me do a little bit of cleaning up action, in a sense that let us try to assess that what we have learned so far in the context of thin film dynamics. So, we have learned how to write the simplified form of the governing continuity and momentum equations, how to write the force balance as well as kinematic boundary conditions, and how to arrive at a pressure scale which is a function of the velocity scale, but the velocity scale is not yet known to us. So, the key question is what is the velocity scale? To understand what is the velocity scale, we should ideally non-dimensionalize all the equations, and from the not only the equations, also the boundary conditions, and then we must figure out that what is the physical force in either the governing equations or the boundary conditions which is dominating, and from that we will figure out the velocity scale. So, to figure out the velocity scale, we need to have either a scaling analysis or a non-dimensionalization. Non-dimensionalization appears to be algebraically little bit more convenient, because you can use those non-dimensional equations to further solve for the film thickness. So, we will now concentrate on non-dimensionalization of the thin film equations. And boundary conditions whatever. So, we will start with the continuity equation. Remember that along the length scale of the problem is LC. So, x dash is of the order of LC, y dash is of the order of h naught, u dash is of the order of UC, P dash we will come to P dash in the momentum equation, P dash is of the order of PC, which is a function of UC. What is that? Mu UC by epsilon square LC. Okay. And not only y dash is of the order of h naught, h dash is also of the order of h naught. Okay. We will consider sigma dash is of the order of sigma naught. What else? I do not think we have any more variable other than this. Of course, we have the disjoining pressure, but it involves its own variables. So, this will be, so now we will convert the dimensional variable to dimensionless variable. So, you will define x is equal to x dash by LC, y is equal to y dash by h naught, h equal to h dash by h naught, u equal to u dash by UC, p equal to p dash by PC, and sigma is equal to sigma dash by sigma 0. V is there, right, V we have missed. So, V prime and Vc is epsilon uc. Okay, where epsilon is H naught by Lc. Okay. So, let us keep this in one side of the board, because we will require this for expressing the equations and the boundary conditions in a dimensionless form. So, this will be just how to do it you can. So, there is a simple way and there is a little bit more methodical, but time consuming way. So, what is the time consuming way? Time consuming way is you can write this as using the chain rule. So, this is, now you go to the definition, this is UC and this is 1 by LC. Simple way is, this can be non-dimensionalized by multiplying with, in the numerator velocity scale, denominator length scale, because this is velocity by length. So, same UC by LC into, so what will be this? Vc by H naught Now, we have already seen from the order of magnitude analysis that UC by LC is same as Vc by H naught, because Vc is defined as UC into H naught by LC, that is epsilon. Therefore, UC by LC and Vc by H naught, these two terms cancel. So, you will get this continuity equation, same in dimensional and dimensionless form. Okay. Next, we will consider the x momentum equation. So, I am erasing the continuity part of it. So, 0 is equal to plus okay. So, by following the same style that I have done for the continuity equation, so here it will be Pc by Lc actually this, when we write it as rho g sin theta, it becomes little bit restrictive, because we are considering gravity as the only body force. So, instead of that, let us write a general body force which could be gravity or something else. So, let us call this as Fx dash as an example. As an example, this is Fx dash, but you could have electric field, magnetic field, so many other effects. So, then if I write a general formulation for Fx dash, you can use that also for solving your problem. So, then now you can see that Pc by Uc is equal to mu into Lc by H naught square, right. Actually by equating these two only Pc and Uc relationship was established. So they are equal. So what we will do is we will multiply the right hand side with Lc by Pc, so that these two terms become 1. So 0 is equal to minus so this one what it will become, Lc by Pc, Pc is mu Uc by epsilon square Lc, right. So this is the x momentum equation. If theta equal to 0 and no other forces are present, so this term Fx dash itself will be 0. Then y momentum equation. So y momentum equation will be something like this. So here also we are considering it as Fy dash, that is minus rho g cos theta, if it is a gravity force. Now we non dimensionalize this, so minus Pc by H naught so 0 is equal to minus del p, 0 is equal to del p del y plus Fy naught into H naught by Pc. So this will be H naught by Pc is mu Uc by epsilon square Lc. And H naught is epsilon into Lc. So this will become Fy dash into epsilon cube Lc square by mu Uc. Right. So please make a note of these things, because in many of the scenarios the body forces along x and y will be governing the physics of the problem, in perhaps in most of the practical scenarios, either body force along x or body force along y. Therefore it is important that we recognize that, see, what if the body force along y is important, what you have to consider, this term is already normalized by its own scales. So this is of the order of 1, because pressure is normalized with respect to its characteristic scale, y is also normalized with respect to characteristic scale. So if this is of the order of 1 and this equation has to be satisfied, then this is also of the order of 1, and that will give you what is the velocity scale. So in this way depending on what is the physics governing the problem, you can actually arrive at the relevant velocity scale for the problem. So, we have arrived at the various governing equations. Regarding the boundary conditions, today we will consider the simplest one to algebraically deal with, that is the kinematic boundary condition. So, kinematic boundary condition. Kinematic boundary condition, we do it in this way. So, V dash at the interface, right. So, V dash is V into Vc, this is H naught by Tc into Tc is what? UC by LC by UC. So, this becomes V in Vc, you can write epsilon into UC is equal to H naught by LC is epsilon UC del H del T plus H naught by LC is epsilon UC del H del X. So, epsilon UC gets cancelled from all the terms. So, you can write V okay. Now, what I have written actually it is not the most formal way of writing it, but it is a very practical way of writing it. Why it is not the most formal way is because epsilon, the smallness of epsilon is already inbuilt in this writing. So, a more formal way is you write u equal to u naught plus epsilon u1 plus epsilon square u2 like that, v is equal to v naught plus epsilon v1 plus epsilon square v2 like that. In the limit as epsilon tends to 0, this is called as asymptotic expansion with respect to epsilon. In the limit as epsilon tends to 0, all those terms will be gone. So, u in the leading order will be represented by u naught, v in the leading order will be represented by v naught. So, here these are the leading order u's and v's, h's and so on. So, by presuming that epsilon is already tending to 0, we are actually here writing the leading order terms. That is the more formal way of writing it, but we will be a little bit informal because we have to an informal way of writing actually can keep you alert about the physics of the problem. So, the alertness that should come about the physics of the problem is already we have considered epsilon as a small number. So, this is the kinematic boundary condition at the interface. So, to summarize, today we have discussed how to non-dimensionalize the thin film governing equations and how to non-dimensionalize the kinematic boundary condition. Of course, there are tangential and normal stress balances which need to be non-dimensionalized. Also, before we take up a formulation of the final formulation of the thin film problem, and that we will take up in the next lecture. Thank you very much.